When we build models of human populations, we assume the raw data represents physical reality. But pull back the layers of any national census, and you don't find pristine biological facts. You find noise, massive, predictable waves of human behavioral artifacts baked right into the numbers. To map the age and sex distribution of a society, demographers use a population pyramid. In a perfect dataset, this shape tapers smoothly from the youngest at the bottom to the oldest at the top. This 1871 population pyramid reveals violent sawtooth spikes at 5- and 10-year intervals, a massive surplus of 30, 40, and 50-year-olds. This isn't a baby boom. When people without formal documentation guess their age, they round to multiples of 5. Demographers call this age heaping. Spotting these spikes on a graph is easy, but visual inspection is useless for predictive modeling. If you ingest this raw data into a municipal planning algorithm, the downstream policy will fail.
You have to mathematically calibrate the distortion first. Age heaping dominates historical datasets, but it remains a persistent obstacle today. It appears constantly among older populations, rural communities, and migrant groups operating outside universal civil registration systems. When calculating age-specific rates with uncorrected data, the math breaks. A false spike of 50-year-olds skews the denominator, warping economic forecasts. Before raw demographic data can be quantified and filtered out, demographers rely on two specific mathematical algorithms to diagnose this exact pathology: Whipple's index and Myers' index. Mastery of these indices stops you from blindly accepting flawed data. It is the mechanism we use to scientifically extract ground truth from human estimation. We start with Whipple's index. Think of this as a rapid triage test, a blunt instrument designed to detect severe bias toward ages ending in 0 and 5. The underlying logic here is straightforward. Across any large, evenly distributed adult population, the ages ending in a 0 or a 5 should account for exactly 1/5, or 20% of the total group. Whipple's index calculates the ratio between reality and expectation. The numerator is simply the sum of the observed population counts for everyone who reported an age ending in 0 or 5. We then divide that observed sum by the expected 20% of the total population in that age bracket and multiply by 100 to scale it. Let's apply this to a South African survey sample of 20,000 adults. If the data were perfect, exactly 4,000 people would report ages ending in 0 or 5. But in this specific survey, 6,000 people did. Divide the observed 6,000 by the expected 4,000, multiply by 100, and we hit a Whipple score of 150. The United Nations classifies any score under 105 as highly accurate. A score of 150 falls deep into the rough category. This data cannot be analyzed as is. It mandates aggressive statistical smoothing. But Whipple's index has a critical blind spot. It only tests for 0s and 5s. It tells us nothing about the reporting accuracy of digits 1 through 4 or 6 through 9. To map the entire error, we need a comprehensive diagnostic, and that brings us to Myers' index. This is an exhaustive audit protocol that evaluates preference across every single terminal digit, 0 through 9. Myers' index operates on a single foundational axiom. If age reporting is flawless, the final digits of everyone's age will be evenly distributed. Exactly 10% of the population will have an age ending in 0, 10% will end in 1, and so on. But when we look at actual survey data from a rural district in the Eastern Cape, the distribution is chaotic. The percentages scatter far above and below that expected 10% baseline. To measure this chaos, we calculate the raw deviation for each digit. We simply take the observed percentage and subtract the expected 10%. Look at digit 0. The survey observed 14.95%. Subtract 10, and we get a positive raw deviation of 4.95. Zeros are heavily overrepresented. Conversely, look at digit 1. It only hit 8.76%, creating a negative deviation of 1.24. Ones are severely underreported. You might think the next logical step is to add all these deviations together to find the total error. That is a mathematical trap. Summing positive and negative raw deviations causes them to cancel each other out. Because the population size is fixed, every time someone incorrectly rounds their age up to 30, It physically removes a person from age 29 or 31. The massive positive errors perfectly balance out the negative errors, pushing the final sum toward a false zero. If you look only at the raw sum, the data appears flawless. We have to mathematically transform these numbers to reveal the true magnitude of the distortion. The solution to this canceling effect is finding the absolute deviation. Absolute deviation ignores whether an error is positive or negative. It only measures the magnitude of the mistake, stripping away all negative signs. That negative 1.24 deviation for digit 1 simply becomes a positive 1.24. We are no longer measuring the direction of the lie, only its size. When we sum these absolute values across all 10 digits, we get a total distortion score of 16.66. But there is a second major trap hidden inside this new sum. We have accidentally double-counted the error. Think about the physical mechanics. When a single respondent rounds their age from 31 down to 30, they create two separate statistical deviations. They generate a -1 error in the ones column and a +1 error in the zeros column. Because we took the absolute value to prevent them from canceling out, our algorithm just counted that single human mistake as two distinct points of distortion. To fix this, Myers's algorithm employs one elegant final step. It divides the absolute sum by 2. This perfectly corrects the double-counting artifact. We take our absolute sum of 16.66, divide by 2, and yield a final Myers index score of 8.33. This single digit empowers a demographer. With it, we can objectively classify the survey data as excellent, acceptable, or problematic, locking in its reliability before a single predictive model is run. Mathematics aside, these indices are ultimately tools for understanding the physical movement of massive human populations across geographic borders. Demographers use a technique called cohort analysis to track a specific birth group across successive censuses, usually 10 years apart. Suppose you track a large cohort of 20 to 24-year-olds in a 2011 census. Logically, they should reappear as 30 to 34-year-olds in 2021. But what if the numbers don't match? What if the cohort drastically shrinks over that decade? You are faced with a strict analytical dilemma. Is this missing group a data collection anomaly or evidence of a physical demographic event? In South Africa, this exact pattern appears frequently. A sharp drop in young adults in rural provinces often reflects immense youth labor migration, as thousands move from the Eastern Cape to the economic hub of Gauteng. But you cannot claim internal migration as the cause until you mathematically eliminate the alternative. You have to deploy Myers Index to prove the missing cohort wasn't simply erased by thousands of 34-year-olds incorrectly rounding their age up to 35. Diagnosing and smoothing age quality is never optional housekeeping. It is a mandatory foundational step. Mastering these algorithms ensures our models actually reflect ground truth. Without them, we aren't planning municipal funding, infrastructure, and national policy based on reality. We're just budgeting for human error.